here, these are the 4 regions. But they're all going to be recording the same information. So if you want, you can think about these as kind of storing 4 different parts of a 4-partite GHZ state. That would be a very simple example of this. But the most general version is just that this observable Z lives on the R sub zth region. It has some eigenvalues. The eigenvalues aren't going to matter as long as they are distinct, because this is the non-degenerate part of the observable, and these are the projectors. So these, if it's a degenerate observable, those projectors could be of more than unit rank. Okay, so is it clear what I mean by this? And is it clear that if I had a that this state would be that if this was a 0 and 1 state on each region? Okay. And this is what it would, yeah, sorry, and then this state satisfies this classical correlation that if I project on the 0 here, I just get this component of the total state, and then it will be the same as projecting on the 2nd region or the 3rd region or the 4th region. Okay?
Is there anything, like, this is a very simple example. Are there more complex examples, or are they all basically amount to big GHZ-like things?
No, they're very much not GHZ-like things. So this was the hard part about picking the definition, right? It's always this thing. So in particular, you can imagine that there is, you have a system A tensor B tensor C tensor D, where there is lots, maybe even lots of entanglement, even macroscopic amounts of entanglement between all 4, and yet they still obey this condition. So right away you can imagine something like, think about this. Say we had a 0 0 plus 1 1 plus 2 2 plus 3 3. Now is that what I want? Hold on one second. Here's another way to write it. So if this is the full Hilbert space, it means my state lives so if these are the branches that I'm talking about here, so define this guy. What it says is that the state lives in some tensor product of AI, BI, CI, and DI, where A is the tensor, or the direct sum of the AIs, and B is the direct sum of the BIs. This is an equivalent definition to this.
Yes.
Okay.
And very much a kind of a generalization of the GHZ.
Absolutely, absolutely.
A little more complicated, but the feeling is.
I think he asked if it was sort of like a GHZ, and you said no, but you meant yes.
Yeah. Okay. What I want to emphasize is that these could be volumes, macroscopic volumes that have all sorts of crazy. They share bell pairs.
Yeah.
There's all sorts of stuff going on at the bottom, but we just want to pull out this kind of large-scale structure.
So would something like a spin glass, classical spin glass, satisfy this definition? Where
I don't know what kind of states those take off the top of my head.
okay.
Yeah, I wish I could.
Just say whatever else it has. It's like the fact that what he's saying is recorded in all our heads, regardless of what else we're thinking.
That's right.
And even though it's a small minority of our degrees of freedom, we all agree about him, and that each of our heads is localized.
That's right. And even when people like, people like me and Charlie who are so in tune that we share bell pairs with each other, right? We can still also share this classical information with other people. Okay. So now so we talked about one observable here, right? So this is like one GHZ bit. Now you can imagine many of those bits.
Sorry, what is GHZ?
It's three guys' names, Greenhorn.
Greenberger, Horn, Seilinger.
Yeah, thank you. Greenberger, that's right.
And it's a kind of a cat state with 3 elements, or any cat state.
So you can, the original version is with three qubits, but you can imagine many partites, and you can also imagine many terms, right? It can be 0, 1, and 2.
I think it's cool that part is in partite.
3 partite, yeah.
Part.
I think it's related to particle, right? Yeah. Yeah. Multi. Yeah.
It's okay. I don't want to slow you down.
No. I'm trying to defend the field, but I think you're right. I think it's silly.
Redundant set of observables, you mean it have to be three copies at least, right?
Well, so we're going to fix an M, and that M has got to be at least 3. But just like we fixed we're going to fix a length scale. Oh, sorry. Let me emphasize that here. So in particular, if we want to be precise, these observables all have to fit in spheres of diameter L. Then you can show that the set of all then you can show that all redundant sets of observables at the same scale L necessarily commute on the state. Okay? And in particular, these observables, right, can overlap with each other. So if you were thinking about it just a priori, you know, if I told you that I have 5 observables at different spatial places, and one set of 5 and then a set of 7, and they were generally kind of all overlapping with each other, it might be surprising, based off of just what I've told you, that those all have to commute. In particular, one counterexample is a Bell pair, and this is why you have to have m greater than 2. Right, so a Bell pair can be written like that, and it can also be written like this, where the plus minus state is equal to 1 over root 2, 0 plus minus 1. That makes sense? So here, right, the observables would be projecting onto 0 and 1 on the 2 different qubits, and here they'd be projecting onto plus and minus. But this would give you 2 different branch structures, and they would not be mutually commuting. Okay? But as soon as you go from 2 to 3, that stops happening and stops being a concern.
Local like that.
Keep it local. Say again?
In other words, if you were spread out like that and the observables were not local, then you could.
Yeah, so they have to be in these spheres, and the spheres have to be separated, so they can't be. So what do I mean? Well, I can tell you the counterexample. The counterexample is the Shor code, and I can explain that later, but but right now I just want to answer Charlie's question or his clarification. If your regions start to look like this and they become kind of delicately overlapping, then you can start having that they don't commute on your state, and so quantum error correcting codes become a counterexample to this. And so this is why we have this spherical requirement. It's just about getting at least some of the projectors to not overlap with each other, and then from getting some of them to not overlap, you can show that they all commute.
So the assumption is that at least 3 of them do not overlap.
Yeah. So the key assumption is or the key thing that you need is that if you take any 2 observables from one set, they don't overlap with all the observables from another set. That's sort of an unintuitive thing, but that turns out, and the 2 comes from this difference between a Bell pair and a GHZ state. And it really, if you think about the stuff that is recorded out there in the world, this is a really reasonable requirement. That if we shared things in our different heads, that our records of them kind of don't overlap with all of each other's. Okay. In particular, I like this definition because notice, I only assume the microscopic tensor structure of the lattice, but these records can be large on some length scale, and they may be overlapping, and I haven't assumed a preferred system, right? There is no preferred, a priori preferred set of the lattice sites, as John was kind of bringing up. So the fact that these commute means that you can define the branches, again, at that scale L, to be the simultaneous eigenstates of these observables. So we can just say, if you hand me a many-body state, I can hand you back the set of all branches that contain redundant information on them. Yeah, good. So this is
So a typical R random state, there wouldn't be just one, there would be only one branch. There wouldn't be
That's right.
any redundant information.
Or there might be, by accident, there might be an exponentially tiny amount compared to system size.
I guess that's like these hydrodynamic degrees of freedom that you have in the gas that you erased.
That's right. So the gas,
Because that's an exponentially small fraction of all the degrees of freedom.
the hydrodynamic variables are.
Ones where you have the same pressure in different
Right.
parts.
Of course, to have non-trivial number of branches on there, you would need to be in a superposition of two different configurations of the hydrodynamic variables. This we expect to be true for anything that's turbulent, that has a chaotic degrees of the quasi-classical degrees of freedom are chaotic for the reasons I was explaining earlier. Okay, so severe limitations of this is that it has to do with a preferred scale L. The preferred M, which is just the number of copies that you require, is a little bit of a limitation, but one way you can think about it is it just tells you kind of how robust the branches are. So in particular, as you decrease M, no, I was going to say, well, as we increase M, all we're going to return is a coarse graining of the branches. So as we require there to be more copies, we are just requiring coarser and coarser branches. And that's simply because any observable that is recorded M times is also recorded M minus 1 times. Does that make sense? Okay. Okay. Oh, and very, very importantly, this doesn't tell you anything about the time dynamics. So what we want, right, as we said at the beginning, is we want these branches to increase in time and not decrease. If they exist now, they have to decrease at some point in the future if the system thermalizes and gets rid of all this information. Whether they connect reasonably from one time step to the next is not so clear. But what you can say is that they can't evaporate immediately. That when you create many copies of something, at the very least, you can't get rid of this until there's like you have time for information to propagate to the other side of the lattice, or from one copy all the way to the other one, which, so they are at least robust on those sorts of shorter time scales. Okay, why might this be useful? So I think I have this slide and one other slide that is going to discuss possible applications to tensor networks, and I will try to. There's only one slide where you actually have to know what a tensor network is. How many people have some rough idea what a tensor network is? Oh, perfect. Okay, good. I'm going to give you all the details. No, I won't. But I just the point is.
You should also
come to an end quickly.
at some point.
Yeah, I think I have 3 or 4 slides left. Yeah, good. So what is the idea here? So we know that tensor networks are and especially, I'm always going to be thinking about MPS states. This is the only thing we really know a lot of stuff for sure. Yeah, sorry, matrix product states, which is a special case of tensor networks on a chain where everything is easiest, one dimension. We know that most states in Hilbert space don't have an efficient tensor network description. Rather, it is the ones that have a low amount of long-range entanglement that tensor network descriptions are useful for. Another way to think about it is that a tensor network description is an expansion in the amount of long-range entanglement, and that expansion truncates quickly if you don't, or it provides a good approximation truncating the expansion if you don't have very much long-range entanglement. Out of equilibrium states of non-integrable Hamiltonians generically generate long-range entanglement. And you know that they eventually have to do this because they eventually will reach equilibrium, and then they have to be hard to describe. And so even when you start them in some sort of nice, clean structure, you will soon your numerical simulation, the bond dimension for your tensor, for your simulation, will have to get too big, and the simulation will get too slow. So the strategy here is that you decompose the states into branches, and so that even if the sum of them has a lot of long-range entanglement, each branch individually will have less long-range entanglement. And then that doesn't really help you, because then you're still keeping track of the sum, and in principle the sum should have an exponential